Hi everyone, we're going to present a work on examining the oblique effect using pattern analysis. My name is Shi, and he's Gung, and this is Donghua. And so the first question would be, what is oblique effect? Ask yourself this question. So, are the two lines really parallel? And if we use a counter-clockwise orientation, how much confidence you have if you oriented with 45 degrees, you can still claim those two lines are parallel with each other. Then what happens if you orient it with 90 degrees? And what happens if you orient it with 135 degrees? And it shows to be the result is this one. So if you collect people's errors on judging whether the two lines are parallel to each other, corresponding to the oriented angles, you can observe that if you orient it with 0 degree or 90 degrees, the error people make is the lowest. But if you orient the images with 45 degrees and 135 degrees, people make the most errors. And also this effect is very obvious in recognition task of contour with specific angle. But if you go to change the task of recognizing the parallel lines into how long do you think the line is, a line length recognition, you can find the variability with the oriented angle changes not as much as this one. So it's not very obvious in one's judgment task. So this is called oblique effect. So oblique effect refers to the performance variation that you give people the same recognition task, but you orient the image with different oriented angles. And this effect has been found in 1861, about 150 years. But until today, people still don't have a formal explanation to this effect. However, this effect is very important in many fields like visual-related design, 3D glasses, virtual reality. Understanding it play a key role in those fields. And fortunately, there is some light from findings in active vision field. Here is a finding from the field, and the eyes make a saccade, means you start from one gaze point and end from another gaze point and go back. That's a saccade. The gaze positions it pass through is not a shortest path, it shows to be. So you can see it's actually a curve. And at the same time, if you compare those curves with the oriented angle of the saccade, you can find that the horizontal and vertical saccade are almost straight. However, the oblique saccade has more variabilities than the horizontal and vertical. So we propose an explanation that we want to connect those two things and to explain the oblique effect. So our explanation is oblique effect is mainly due to less precise eye movement in the oblique direction and the more precise eye movement in the horizontal and the vertical direction. Remember, we want to connect this performance and these findings in active vision, and we claim that actually it's because of this that people have such performance.
So to simulate saccadic eye movements, we used the ocular model named two-dimensional ocular model plant mathematical model. And then we modeled the human recognition process with a multi-class SVM classifier, and I will explain it in a few slides. Finally, we trained the classifier with the input generated by the model above and evaluated the performance. Regarding the ocular muscle model, like I said, we used this model, and it basically has 4 artificial muscles which are variables for the model to generate saccadic eye movements trajectories. So saccade can be categorized into two types, which are positive and negative. The positive one drives our eye rightward, which is controlled by the muscle named lateral rectus. And the negative one drives our eye leftward, which is controlled by the muscle named medial rectus. Like I said, these muscles are going to be variables for the model to generate our data. After we got the data from the model, we use a multi-class SVM classifier. But actually, SVM is intrinsically a two-class classifier. But the problem is, our problem has four classes, which are horizontal, vertical, and oblique left, oblique right. So we have to use a SVM for multi-class classifier. And we use the method called one versus one scheme, which is like a tournament. It's very straightforward. We have 6 SVMs, each of which is for different pair of labels. For example, the classifier on the top is for the label 1 and label 4, and so on and so forth.
So our experimental procedure is as follows. First, we take a set of natural images, and then we use the two-dimensional OBMM to generate the trajectory that the eyes move. And then we use that trajectory, apply on the natural images, sampling the image in 4 types of movement: oblique left, oblique right, horizontal, and vertical. And then we feed in the multi-class SVM classifier is represent the human perception process, specifically the visual cortex, which process visual information of the brain, and then we collect the perceptual performance. So this is how we do. We sampling the images based on the trajectory. As you can see, the vertical, the horizontal movement was taken by assembling 60 times 60 pixel images on a set of 1240 times 1240 images, vertical, and then we turn it to grayscale and collect all the data labeled down with 4 types of movement. We perform 20 generation of trajectory and generate 10 different trials to conduct the experiment. Basically, we conduct 2 types of experiment. One type is moving forward, meaning the eye move from the origin, which have a 0, 0 degree from horizontal upward, vertical upward, horizontal rightward, and then oblique left and oblique right. The second type of experiment, we generate the movement from the current position, which backward to the origin position, and then we do the same thing. After that, we feed in the multi-class SVM and perform 10 trial classification with 2 different types of experiment. This is the result that we collected, the trajectory that we collected from using the 2D OBMM. This is oblique right, oblique left, vertical, horizontal, no, vertical, horizontal from forward from the origin. This is backward movement from its current position, which is 30 degree vertical, 15 degree, 30 degree horizontal, 15 degree vertical. and then move downward. This is the same thing. So the performance that we were able to collect is that horizontal and vertical have significant better performance than vertical. Why the horizontal and vertical have at 90% accuracy, oblique left and oblique right have about 70 to 80% accuracy. The same thing happened to backward movement here. So this is the average performance that we were able to collect. Oblique left, oblique right is very lower than the vertical and horizontal. Following as the statistic analysis of our result was the oblique left and oblique right have more standard deviation, greater standard deviation than the vertical and horizontal happen with both forward and backward. So the explanation for this type of result is that because oblique left and oblique right movement have very imprecise, so it results in very bad sampling images, and it's creating a lot of noise. Why for vertical and horizontal movement, at one point you have multiple sampling of images, so it's increasing the quality of the images. Finally, the conclusion of our project is that experimental results show that human perception of light orientation is more accurate for horizontal and vertical lines compared to the diagonal lines based on the experiment that we result that we collected. The second conclusion is that neuronal motor output plays a significant role in determining the efficiency of perception performance. So normally, the motor learning skill is affected by your perception. So your perception take in visual information and it's help you to learn new motor skill. But we find out that neuronal motor skill also plays a significant role in determining the efficiency. So it's two-way around. Our experiment is very closely related to the actual human perception process, and that it can explain the basis of the oblique effect. And so far as we know, this is the first work ever that trying to connect the research in vision, active vision, and neuroscience that to explain the origin of the oblique effect. Previously, people have no idea what the oblique effects, what the origin of the oblique effects, and they found out that the oblique effect is something that happened inside the visual cortex of the human brain. It is not caused by some impairment of the visual sensor. That's it.
Okay, we have time for one question.
What's the data set you use for classifying, and how many classes are there in the data set?
There's 4 classes: oblique left, oblique right, vertical, horizontal.
So you're classifying those 4 directions?
Yeah, those 4 movements.
For movements, not for classifying images?
No, actually we classify images, but the images that we generate, basically we generate 4 packages of images. Moving left contain a set of images that was able to we was able to collect from the trajectory of oblique red, and then vertical, horizontal, and oblique right. we labeled them, and then we created another set of movement, and then we tested. We change the first set, and then we test the second set. Yes.
So can you go back to the conclusion? I think maybe I'm missing something. For the first conclusion, like you feed the training data set or feed the image that you generated to the SVM. And I can't understand how you connect the classification accuracy to how the human perception of the line orientation. So how the accuracy of the SVM connected to the image perception.
So this is explained using this model here. So the human eye do different type of movement, and the saccadic movement is one of those movements. It sample images. If we move left, move up left here, it's during that time it samples some images, and then the images is fed into our visual cortex brain to do some visual processing, and then it tells us that if we can recognize the images correctly or not.
Then what's the purpose for the SVM?
The SVM represents the classified, the visual cortex.
Why you can, like, how you use SVM to model the human perception process? Why is SVM? Is there a reason to choose SVM?
No, any standard machine learning technique will sufficient for this. This can represent the classification process of human perception.
So is it like treat the human perception process as a learning process, or?
Yes. Basically, if you practice some tasks with oblique effect, some tasks that involve the oblique effect multiple times, of course you will get better, right? So it's the same thing.
I want to add one more explanation. So the reason that we use multicast SVM that so it's when we have enough images, of course, deep learning neural networks will be the state-of-art classifier to be trained and get high accuracy. But if we don't have enough images, now SVM shows very good performance on this. And actually, so this angle means corresponding. So actually, we are actually modeling human perception process by multicast SVM classifier. But our point would be, since machine learning is actually learning how human recognize things and classify things. If you use other classifier, you can also reproduce the oblique effect as we did. It's not very specific to the classifier.
Right, so we are out of time, so you guys can take it offline. So if yeah.